Let me review what we did last time. It's an important transition from relations to functions. So once again, every function is a relation. Not every relation is a function. By the way, what I always say about relations applies to functions, but then functions is a narrow class. They have more specific narrow properties, and so we can say more about them. But what we can say to begin with is about functions is what we say first about relations. So that's a typical relation: x squared plus y squared is equal to 1. What does it have there? It has such things as the it does not have inputs, outputs, but it does have a graph. Okay, so every relation has a graph, and once again, remember how it is done. You pick you pick x and y, and you pick x and y on the xy plane. You can see it to the left, and you keep asking the question: does this pair xy satisfy the equation? Okay, so relation, equation, restriction, condition, all of these words apply the same equally. Except relation is the official one. Okay, so relation is something more specific. So the graph then, and then if it is yes, you plot the point. If not, you do not, and then those points might form something recognizable. As last time, what we discovered that it looks like a kind of a circle, even though it was not obvious whether that circle was an actual circle in the literal mathematical sense as a curve. See that picture on the right, or it's maybe it is thick. How can you tell? And the answer is it's hard to tell. But if we do turn to functions, then graphs of functions cannot be thick, because remember the property of a function is that. Okay, why does it disappear? Because hold on a second. Okay, so I'm trying to. Okay. Okay. Just give me a minute. Yeah. Okay. So what I was trying to say is that what's so special about graphs of functions or functions in general is that there is only one y for each x. Okay, that's the vertical line test that we talked about, which means that the graph of a function cannot be thick. It cannot only be 1 point thin or thick. Well, obviously you cannot go any thinner than that. So if you cross it with a vertical line, it will meet only once at one single point. So that a thick kind of curve, a region, is not possible if it is a function. So that's one of the reasons why we like functions better, because they're easy to plot, they're easy to study, and they do form typically curves. So their graphs are curves. So that is why when we try to solve that equation for y, we realize that it's still not a function but 2. See, y equal plus or minus, and then we would realize that actually each of these two functions actually form where's that graph? Form a circle. Yeah. Okay. So we plotted the two graphs separately, and we ended up with two circles. So if you want to merge those two charts, and you will have a literal circle, maybe with some missing points. Okay. So now. Okay. So let me continue with the review. So now we turn to functions in the narrow sense. I have this here very nice black box. It is really black. So once again, you might not be able to see what's happening inside, which is not important, because it might be not of your concern at all. All you have to know about a function in the abstract, that there is input, it produces the output. The same input produces the same output, and there's only one output for each input. Okay, so and then we proceed on to looking at the functions in different different angles. And graphs is only one of them, so we'll circle back to graphs. But this is I like to start with looking at functions as flowcharts or programs, or what else? How can you otherwise describe it? Diagrams. So diagrams of steps. So certainly it would be no trouble for you to avoid all of these arrows and boxes, and instead of write just a list of instructions. So step 1. Add 3, step 1, step 2, multiply by 2, and so on. So it could be a step of instruction purely in the kind of a language of just plain English rather than some kind of diagram. Okay, but that's fine. At some point, you pick one or the other. So those will be the same. So list of instructions is the same thing no matter how you write it. You can write it from left to right, right to left, top, bottom, very popular. But then the next item is really different from the previous one. It has an algebraic formula, and in fact I probably would emphasize that there's a single formula. Because the previous one it is a bunch of formulas, even though they're kind of hidden in there, but it is a bunch of formulas, in each formula applied consecutively until you reach the end. Okay, the next one it's about the same function, turns out, but you want to have one single formula for whatever reason. So a computer wouldn't care, by the way. So you just give it a list of instructions, and you have your it will do it just fine. It doesn't need a formula or one single formula. It is usually done for people. So one single formula, you want to manipulate the formula by hand, and you want to present it in one formula, and then maybe looking at it, it will give you some insight. Or there might be some cancellation, simplification. So that's why that's algebra is for. So really seeing what's going on in one place. All the intermediate variables are gone. So y and z are gone, and you concentrate on how the input x produces output w. Okay, so not exactly part of this idea of functions, but the order of operations is important to know. So I think there must be one problem on the homework testing that. So it will come up, obviously, again and again. Every time you do it by hand, you need to know how things are happening, and that's from there you can actually create instructions for the computer to compute that function. If you know the list of the order of operations, you don't have to actually carry out those operations as long as you know what they are and what order of operations is. So you turn that one formula going backwards into a single list of instructions. Okay, so that's what the next problem is. From a single formula to a list of instructions, and then you do not have to actually compute the formula, but you ask the computer to do it for you. Okay, but you still have to understand what's happening. Okay, so that's what it looks like. A bunch of formulas, and you just turn the bunch of formulas into the list of instructions. I want to repeat that idea. What might help if you're not sure about how you decompose a formula. You read it from inside out and carry out from inside out. So x plus 3 parentheses multiplied by 2 parentheses squared. Okay, from inside out. It might be more complicated than that when x appears more than once, such as this at the bottom. So then it might be slightly more complicated, but it only seems more. It is actually simpler because there is only one place for x to come in, and there is no sequence of operations, but rather with variables feeding into the next, as we just saw, but rather just you plug in x once, and so each x is replaced literally with the number that you are interested in, and then you have a formula that does not have any x's left. You have only numbers there. The only thing to worry about is to put parentheses. It is easy to make a mistake if I'm supposed to plug in x equals, say, -2 rather, where am I? -2 rather than 2. So x equals -2. If you are not careful, you might end up with something like this. Okay, so that is awful. Okay, so that's if you do something like this. Substitute -2. The negative is what creates trouble. If you don't do it carefully, then creates such a mess. And why? Because what's the way out of it? Use parentheses. Okay, so just the same. So x is not equal to -2. Think about x equal to -2 in parentheses. It's the same thing, right? So -2 in parentheses, same thing. But it will save you a lot of trouble if you just keep parentheses as much as possible, for as long as possible. Then there is no trouble. I have the same formula. So f of -2 is, as we can see, -2 is in parentheses anyway when you use the notation. So 2 -2 in parentheses squared minus 3 -2 plus 7 over -2 in parentheses cubed minus 5. Okay, so that box is the parentheses. Just instead of having them rounded, they're kind of like this squarely parentheses, like brackets. Okay, so it's the same idea, and you just try not to be. Ask yourself what I'm writing, is it ambiguous or not? Okay, is there a way to misunderstand it? And if there is or maybe you suspect there might be, well, put parentheses there, and then the ambiguity will be gone. Okay. So once again, this is metaphorically what we're talking about, how notation appears. Name of the function, the name of the input and output, and then those parentheses serve as funnel, as where you put the input x, okay, which could be a letter, it could be a number, and that's sometimes one of the problems. I think asks you to not to put a number in place of x, but another variable. Okay, another variable with maybe some computation. So it is a substitution from what we just did in the previous example. So I might ask you to compute f of say u squared. Okay, so same function is this, and then you're supposed to compute f of u squared. Just understand first that it is entirely about once again substitutions. So it doesn't matter what you can substitute anything you want once you have a formula. Substitute it as long as, once again, be careful and use as many parentheses as possible. Okay, so we have, once again, so I take my either formula algebraic on the left or that diagram on the right, replace each x with u squared in parentheses. Okay, so 2 u squared squared. See what I did? I replaced x with u squared in parentheses. Okay, so this is my box. This is the box that I have. Whether it is a box, real box or not, this is what I have here. So x is u squared, and so I replace it with u squared in parentheses to separate whatever. I haven't done any computations. I do substitution. Literally, I'm substituting one for another without doing any algebra. Once you have the formula, you will do your algebra if necessary. But to begin with, you don't. You just do substitution very carefully. So -3 u squared in parentheses plus 7 u squared in parentheses cubed, what is it, minus 5. Okay, intentionally, I'm not going to even try to simplify it. Well, imagine that, maybe I don't care. Okay, so once again, every x appears 3 times, replaced with u squared in parentheses. So then the substitution is finished. That's the point. So you had a function of x, now you have a function with x replaced with u squared, and then, as I said, do you continue on? Maybe. Maybe not. The point is that the hard part where the mistakes happen typically is the substitution part. And this is how you do it, and then you simplify it if you feel, depending on what is the purpose of the problem. So any questions about this? Okay, so then those are 2 interpretations: a list of instructions, a single formula, algebraic formula, and now 2 more interpretations of functions. It is data and graphs, closely related. So the data, meaning that it cannot contain as much information as the formula, because data is the table, and you cannot have infinitely large table. So even I put here just a few rows, so I have 5 rows here, and then I could have 100. The Excel might handle thousands of rows, but there is the end somewhere. Even if you have a computer and it produces data, unless you have infinitely long period of time, and say you can imagine that suppose my input is time and the output is say temperature. Okay, then hypothetical, if you have infinitely long time to wait, you can have infinitely long table. Okay, and that would be an infinitely large table with a function that with infinitely many possible inputs. Okay, but that's not realistic. So realistically, that's what you see. A table that may be short, may be long, but that's it. Okay, so that way, these are very small functions containing very little information. In comparison, you can imagine. Once again, I try to do it here. Well, let me make that point. How many values I could think of when the function is given by either the list of instructions or by a formula. Well, there is no limitation, or almost no limitations. I can plug in any number x into this list of instructions and work out my way towards y. Yeah, I certainly cannot carry it out infinitely many at the same time. So if I want to produce a table, it will still be a short table inevitably. But hypothetical, potentially, this contains infinite amount of information about the function. Same with the formula. I can plug in any value I can think of, and there's a chance that it will work out and give me a y. There is a possibility that it won't work out, but if it does, then you have infinitely many data points. Okay, and here I have only 5. Okay, so that's the limitations of data. Either you're speaking of functions that is small on its own to begin with, or what it is a snapshot of a function that is bigger, and you're just skipping values. Okay, same with the graph. You're plotting the data on in the table, and then once again the assumption is that you are skipping values. Okay, so presumably there is nothing wrong with a function with neither one of these functions. So you quite possibly have that. We saw it. Well, in fact, here it is, to remind you what we did not long time ago. Let's keep doing it. Not long time ago. Not this one, not that one. No, yeah, this one. Okay, so very few inputs, very few outputs, and then that table highlighted over there is that table of values of the function. Column for x's, columns for y's. That is the table representation of the function. And then if you now go horizontally and you plot these 5 points, 1, 1, 2, 1, 3, 2, and you have the graph on the right. So it is quite possibly a function that you're interested in, containing only just a few points. Now, but what if it is a snapshot? It is possible that a snapshot is actually what the reality is. It's just some information. So, so even though there is nothing wrong with a function like that, it is possible that there is more to it than meets the eye. And there is Excel does makes this for you. It might try to guess. Excel supplied with those 5 points. There's an option that Excel will try to guess for you what is that there might be something bigger than those 5 points behind the data. So maybe there is some kind of process that is actually continuously changing from one point to the next. Okay, and then it gives you this guess. There is nothing special about this guess because, for example, this is also a guess. So which one of these 2 guesses is better? I don't know. It depends on the circumstances. This is the data. And these 2 are just the 2 guesses. Okay, and in fact, you can end up with this, but you know, you could try to create a smooth curve. It is possible. So actually, this requires some calculus in order to carry out something that smooth-looking curve. This is the simplest one. Just connect the points, and you have your function. That's called interpolation. Now you heard this term. Right, so if you have 2 data points, you try to figure out what's happening in between, and there are many options to do it. If you have only 2 points, then what's the best guess? The best guess is just go straight line, right? So, and then, or alternatively, you can imagine that what happens is we actually did it a couple of times. Instead, you are getting more and more data that doesn't go to infinity, but rather you divide the interval into smaller and smaller intervals. So, for example, there will be another point over here, an extra point over here, extra point over there somewhere. Okay, and so then the density of points become higher and higher, and then without any help from Excel, it might actually turn into a curve. So this one is almost a curve. Well, that's not the one. This one is closer and closer to the curve, and you can imagine that if you zoom out, it definitely is almost a curve. So you get twice as many points. The dots are so large that it will start overlapping, and you have a curve. So all of these are possibilities that we have to keep in mind in order to deal with functions. Okay, so now the big topic that I was overlooking here on purpose, obviously, is domains, and what it means is that a function is not a function without a domain. Okay, what is a function? Well, I don't want to go into the definition, but it includes the domain and codomain. Remember those sets that we called X and Y. So the notation is actually frequently used. Notation. F from X to Y. So once again, X is domain, Y is a codomain, and then the idea is for each X in X, there is a Y in Y. Okay, so that's a function. Inputs turns into output somehow. Okay, and so then what is that? How then does it make any sense to have a discussion, as we just had, about a function without specifying its domain? And the answer is that you could, but you better quickly get the domain as quickly as possible. Okay, so you do need the domain, even though you can't start discussion about the function without having the domain specified. So so when a domain is not specified, well, specified. Okay, so depending on what is that you do have, typically what you're facing is one of those four ways to describe functions. So once again, a flowchart, or well, better probably, I prefer to describe it, probably better to describe it as a list of instructions. Algebraic formula. Thirdly, a table with 2 columns, and number 1, graph. Okay, so then if that's what you have for a list of instructions, where is the domain? The domain is not specified. So then you have to add to these, add the domain. So in other words, allowable values of X. Okay, so it's especially straightforward with the algebraic formula. With the other two, well, let's look at the last ones. The last ones is you look at your table, and then whatever is in the first column is your domain. Okay, the codomain, however, is usually just chosen to be, well, let's concentrate on the domain first. So just the first column will be your domain, the end. Okay, so that's the easiest way to solve this problem, is just to say that the first column contains the x's is the list of elements in your domain. Okay, with the graph, suppose you have the graph but you don't have the table. So you have to look then at the at the appropriate values of x. So it is, if you have a smaller graph, it might be easy. Where's that one? Yeah, okay, so you just look at it. This is your graph. Suppose you don't have the table. You just look at the corresponding values of x, and that will be your domain. Okay, 1, 2, 3, 4, and 5, and that's your domain. Okay, so if it is one point at a time, there should be no trouble with that. The problem of finding or specifying the domain is usually about the formula of part 2. Okay, so once again, how do you specify the domain for an algebraic formula? So you got to figure out for which values the formula makes sense and for which it does not. So in other words, what we're talking about is so for a formula, find the largest possible domain. So the problem is slightly different. Largest possible domain, because they are domains for the same formula. There might be different, for the same formula, you might provide different domains. It's up to you. Depending on what kind of problem you're solving, the domain might vary. Remember the problem with the farmer, right? So the function we're talking about was a function of the area of the enclosure as a function of the width of the enclosure, okay? So then, but the problem only, whatever, the formula was very simple. I believe it was like a W50 minus W, something like that. Okay, so it doesn't matter what number I plug into the formula, it will make sense, it will work out, but mathematically. But for the farmer, it only makes sense when physically, when the width of the enclosure cannot be negative. Okay, and it cannot be also larger than 100 feet or yards rather of fencing, because you don't have more than that. So then you put the nature of the problem sets limitations on your domain. So that's one way to look at it. But if you do it in a purely mathematical sense, then that's how we do it. There is formula, nothing else. So there is no real-time situation for us to worry about. So what do? We look at the formula itself, because there is nothing else. So this formula then would be domain is, well, the largest domain is negative infinity, infinity. Once again, every value you plug in will give you legitimate output. So the largest one is called the natural domain or the implied domain. So in other words, the formula carries with it the domain. So even when it is not specified, it can be extracted, and when it is not specified, then the assumption is that it is the largest possible. So you don't want to, you want this formula to be as applicable as possible, so you make the domain as large as possible. Okay, so that's why it would be no trouble for me to have the domain for 0 to 100 as we had in that problem, because these are only the numbers for the width of an enclosure that make sense. But if we are free from that and we're just doing mathematics, then we take the largest one, and it is called the natural domain or the implied domain of the formula. Okay, so have you seen domains before? Domains in this sense? Domains of functions. So as you can see, I put here a domain of formula, even though sometimes they say it is the domain of a function. It is either one is fair, but it is without the domain. Technically, formula is not a function without the domain. Okay, but since we can find the domain in this kind of a standard way, then implicitly that domain is present there. So that is okay as long as you're prepared to do this extra work. So as examples, a couple of examples would be, you ask pretty much what can go wrong. Okay, so we're talking about largest possible domain. Well, what does it mean? It means that find all x's for which the formula makes sense. Okay, so that's the largest one. So you check out one x at a time, and if it is, you plug it into the formula. Does it make sense? If it does, then you include it in the domain. The idea applies equally to the list of instructions formula. So you hypothetically, you can also try to every x plug it into the list of instructions, see if you can follow the instructions all the way through without breaking down, and then you say, well, that's my natural or implied domain. Okay, so what can go wrong? As you certainly know, what can go wrong in algebra? What's most likely to go wrong in algebra? Algebraic operations. What algebraic operations are not legal? Well, you remember any occasion when you do something and then you were told that you cannot do that with numbers, some numbers?
Would it be depending on the situation? You can't have negative numbers.
That's right. Yes, but that's right. That was my second answer. But there's a simpler one before we get to that one. When some negative numbers don't work out as well as positive. But what is the simpler example of what you're not supposed to do in algebra? Well, we'll go down the list of what you can do in algebra. So there are 4 algebraic operations: addition. So 2 numbers adding together. Can you take 2 numbers of any 2 numbers? Can you add them together? Yes. Can you subtract them? Can you multiply them? Can you divide them? Can you divide them? Can't you think of an exception? That's right. So you cannot divide by 0. So can't divide by 0. So that's division is an exception that. Inside of that exception is an exception of 0. You can divide any 2 numbers hypothetically, but as long as the second one is not 0. Okay, so that's the only exception. That's the number one of things that can go wrong that you are not allowed to do in algebra, and that is actually also it happens more often than you think with computers. The computers don't catch fire or explode when they divide by 0, but it's close enough. And the problem with computers, they have only limited accuracy. Okay, so it means that if your number is not exactly 0, it just gets close enough to 0, then computer cannot tell it apart from 0, and then it divides by 0, and then it loses pretty much track. Then whatever follows is meaningless, or because well, you cannot divide by 0, so it will just tell, well, I crashed, and now go figure out what went wrong. So like I said, it happens more often than not, and that's why to get around those problems, you have to be careful about what you tell the computer to do. Not only don't divide by 0, which is kind of obvious, but don't divide by a number that is too small. You can try it with the calculator. Divide by a number that is 0.000, and you have 10 zeros, and then 1. Okay, so it's not 0 technically, but if you try to divide, you might see some trouble. Okay, so in the second one is some negative numbers don't apply, and that is we are going beyond the 4 operations. of algebra and proceed to, like, from elementary school to maybe high school, square root, for example. So I can't take square root of a negative number. Okay, so there is a caveat here, is that you can, if you're willing to deal with complex numbers. And we have to face them eventually. So later in the semester, we'll have to talk about complex numbers. But for the time being, we stick with real numbers. And with real numbers, we're simply not allowed to take square root of a negative number. So square root of negative 1 is undefined. And every calculator will pretty much break down if you ask it to do it. So these are two main things at the very top of the list, the things that can go wrong in algebra, and that these are the two things to watch out for when you're looking for the natural domain. You have a formula, and then you look at it. Is there any division somewhere? If there's any division somewhere, and then you have to exclude those numbers, those inputs that produce division by 0. So, for example, if I have f of x is equal to 1 over x, I discover division right away, and then undefined if x is equal to 0. Okay, and then you certainly, this is a pretty good explanation of what you're facing here, but the problem typically is more narrow, more kind of a rigorously defined, and the question is find the domain. That's how it is usually put. The same idea, but more specific. Find the domain, or the natural domain, if you want to be careful here. Natural domain of f of x is equal to 1 over x. Okay, so then the answer is you have to point out what that set is. Remember, the domain is a set, so you have to be specific. You remember, we studied that set building notation in order for us to be able to produce these sets on demand. And so you can still use just words. And how would you verbally describe the answer? No, I don't want to say undefined. The answer is that what is natural domain. So your answer should be the natural domain is. The natural domain is. In fact, you can go on and say the natural domain is the set, and then you describe what that set is. So what is that set? We already have the answer. We just have to restate it in a way that would be in line with this language. So what is the set? It's so you sort of turn it around. You know, we have found for which value of x the function is undefined. Turn it around. Now we want to say for which values it is defined. All real numbers but 0. Okay, so the set of all real numbers but 0. That would be the proper way to answer it verbally. Then you can still try to use the set building notation. So that's another way to answer it. So let me write this right. So domain is, natural domain is x not equal to 0. That's probably the easiest one. So set building notation in braces, x column, and then the condition that x is supposed to satisfy. So as long as it's not equal to 0, that's the only condition that there is. X not equal to 0, so that's the answer. Okay? There is yet one more way to answer it, and that is with the interval notation. So domain is, let's visualize it before we answer. We could try to visualize it. It's really easy to visualize it. This is my real line, and I include everything. I have to exclude 0, but I include everything else. So I can visualize it like this. So the green is the domain. Okay, so then the domain, what is the domain made of based on this little picture? It continues on to infinity one direction and infinity to the other direction. So what is it?
All real numbers except
Yeah, well, yeah. What I'm driving at is I want to use the now different notation, and that's the integral notation. Remember the integral, because do you see integrals there? Right? You see the integrals? In the whatever I marked with green is made of integrals. What integrals? Do you see any integrals there?
Are you speaking of the different types of brackets?
Yeah, just any. So there are two. Look at it. That's you just point out the integrals first, and then you find notation for them. So one is to the left of 0. Everything to the left of 0 is in the domain, and then everything to the right of 0 is also in the domain, right? So what remains is just to recognize that these two are, in fact, both of them separately are integrals. So once you recognize them as integrals, then you probably want to use that very compact notation in order to point out what they are. So what is the first integral? How do you write it? Yeah? Comma.
And then positive.
No.
But how are you going to exclude 0?
No, there are two integrals, so one at a time. So let's take the left integral. How far does it go to the right? No, to the right. So we take the first to 0, right? It goes up to 0 like this, right? So the first integral goes from negative infinity to 0, and then it stops. And then we look at the second one. It starts at 0 and then goes all the way to infinity. As you can see, I'm using circular parentheses to indicate that they're not, the 0 is not included. Okay, so I just have two of these, and I have to include both. The notation that we haven't used, but you probably can, you may remember. If I want to include two of these sets together, what notation do I use? U, that's right, which stands for the union. And it includes both, right? So that's the additional way of forming new sets, is to combine them together in this fashion. So it includes both in the first, all the points in the first set and all the points in the second set. So that it is, in fact, kind of looks longer than the original, but it is actually it is kind of visual, right? If you're not talking about what is being excluded, but rather what is included, and the notation repeats the picture pretty closely. It's just algebraic way to represent this picture. So, and then there are you might face problems that are very similar in nature, but just more algebra to worry about. Say f of x is x, or let's hold on a second. Say 1 over x minus 1, x plus 1, x squared plus 1, like that. And once again, you have a bunch of divisions here. So you have a function with a big fraction with a denominator which depends on x, and there are many possibilities how this thing can turn into 0. Okay, and so each of those possibilities would have to be taken into account, and then when you write, the answer is what is the natural domain. So the question is still the same: find the natural domain. This, okay, and so what do you have to look out for is you ask yourself. So when it is undefined, when is this undefined? And one quick answer, so it would be not complete, but the quick answer is whenever the denominator is 0. So in other words, denominator is equal to 0. So that whole fraction, so whole expression here is simply written as an equation. So these are the values, all values of x that satisfies this equation would have to be excluded from the natural domain. Okay, so you might face more complex equations But for this one is for our convenience, it's already been factored. So you can just read these factors and tell what values to exclude. Can you tell me what values to exclude?
0.
Okay, x equals 0, because it will make the first factor 0. Okay. What makes the second factor 0?
Positive 1.
Positive 1. And the next one?
Negative 1.
Negative 1. And the last one? What? No, not of 0. What x will give you 0 will make the last factor equal to 0.
Oh, maybe.
Yes, yes. So what is it? Well, if you're not sure, you just take x squared plus 1, set it equal to 0, then you have x squared is equal, and solve it. Negative 1, so x is equal to what?
Square root of negative 1.
Which is what?
That symbol, negative 1.
Undefined, that's right. So if it's undefined, because it's not a real number, so the answer is there is no such number. Okay, so we don't have to worry about that x squared plus 1, as long as x is real, will never give you 0. Okay, so that's the good news. So these are the only one that you have to exclude. So the answer is all reals, but 0, 1, negative 1. If you want to visualize it, you take 0, negative 1, and 1, and you have, as a result, you have your domain is made of 3 intervals, like this. Okay? All right, so we'll talk more about this next time.
2 questions.